Hi, in previous lecture I discussed DFS, depth first search, its different timestamp like discovery time and finishing time, its algorithm with its running time. In today's lecture I will discuss what is depth first forest, different type of edges of depth first forest and some examples. If that is one component, then we'll create a depth first tree. If there are more than one component, then it will create a depth first forest. And there are four type of edges. First one is tree edges. Tree edges are the edges in depth first forest. Edges UV is a tree edge if V was first discovered by exploring edges UV. The original edges present in depth first tree is called as tree edges. Next is back edge. Back edges are those edges UV connecting a vertex U to an ancestor in the depth first tree. If one node is connecting to its ancestor, then it is a back edge. We consider self loop which may occur in directed graph to be a back edges. Next is forward edges. Forward edges are those non-tree edges UV connecting a vertex U to a descendant in the depth first tree. Next is cross edges. Cross edges are other edges that can go between vertices in the same depth first tree at the same depth as long as one vertex is not an ancestor of the other, or they can go between vertices in different depth first tree. So tree edges are present in depth first tree. Back edges, the edges from one node to its ancestor. Forward edges, the edges from a node to its descendant. Cross edges, if one node is not ancestor or descendant of the other, then there is a cross edges. Let's discuss example 1. First I'll create a undirected graph, then from that graph I'll do DFS. For depth first traversal I need a stack. Let me start the traversal from a vertex. I'll write 1 here. 1 you can say as the discovery time or push time. I'll push A onto the stack. Then from A I can visit B. Here I can write 2. 2 is the discovery time and I'll push B onto the stack. Next from B I can visit D. Here discovery time will be 3 and I can push D onto the stack. After D I can visit H. Here I'll write the number 4, that is the discovery time, and I'll push H onto the stack. After H I'll visit G. I'll push G onto the stack and I'll write number 5. Then from G I can visit C. I'll push C onto the stack and I'll write number 6. Then from C I can visit F. So I'll push F onto the stack and I'll write number here 7. Now no adjacent left for F. F adjacent is H. H is already in stack. We already visited H. So what we'll do? We'll do backtrack. From F we'll do backtrack and I'll write here 8. 8 is the pop sequence. And I will also pop F from the stack. And I will check is there any adjacent left from C? No. C adjacent is A and G that already visited. So we'll write number here 9 and we'll pop it. We'll backtrack to G. Again we'll check is there any adjacent left for G. Its adjacent are C and H that already visited. So we'll pop this G from the stack and I'll write number here 10. Next I will backtrack to H and I will check is there an adjacent left for H? Yes. So H adjacent is E. From H I will visit E. I will write number here 11 and I will push E onto the stack. Now is there an adjacent left for E? No. So I'll pop it. I'll write number here 12, that is the finishing time. Then I'll pop H and I'll write number here 13, that is finishing time for H. Then I'll pop D and I'll write number here 14. Next I'll pop B and I'll write here 15. Next I'll pop A and I'll write here 16. So I traverse from A to B, then B to D, D to H, H to G, G to C, C to F and F to E. These are its discovery time and finishing time. we are assigning two timestamp or two ordering of number. First one is for discovery time and second one is the finishing time. Or you can say one is push time and other is pop time. In previous lecture I discussed timestamp will range from 1 to 2 multiplication vertex. There are 8 vertex. 8 vertex, so range will be between 1 to 2 multiplication 8, that is 16. Here the push number or discovery time is 1 and pop number or finishing time is 16. So the timestamp range between 1 to 16. Timestamp range between 1 to 2 multiplication number of vertex. Depth first traversal is not unique. There are different type of depth first traversal possible. How you are traversing. Some more depth first sequence are like from A you can visit B, from B you can visit E, from E you can visit H, from H you can visit D, then from D you can backtrack, then from H we can visit F, then from F we can visit C, and from C we can visit Z. There can be another sequence also. We can start from H. From H we can visit G. From G we can visit C. From C we can visit F. Now we can backtrack from F, and from C we can visit A. From A we can visit B. From B we can visit D. Then we can backtrack, and from B we can visit E. There can be another DFS sequence also. From A we can visit C. From C we can visit F. From F we can visit H. From H you can visit G, then from G you can backtrack, from H you can visit E, from E you can visit B, from B you can visit D. So DFS traversal sequence is not unique. There may be more than one DFS traversal possible for the same graph. Now you understood how to do DFS traversal. Let's discuss how we'll construct DFS tree for the same graph. So I will do DFS tree for the first sequence. For this sequence, for which I discussed the timestamp. From A you can visit B. So B will be child of A. Then from B you can visit D. Now D will be child of B. Then from D you can visit H. H will be child of D. Then from H we can visit G. So G will be child of H. Then from G we can visit C. So C will be child of G. Then from C we can visit F. Now F will be child of C. Now from F we'll backtrack to C, then from C we'll backtrack to G, from G we'll backtrack to H, and from H we can visit E. E will be child of H. Now this is the DFS tree for this graph. All the edges given in DFS tree are tree edges. Let's do the back edge or forward edge or cross edge. This is a undirected graph. In case of undirected graph, there can be tree edges or back edges. Maximum time we do back edges, that you can also do for forward edges. Now which edges we use in DFS tree? Like this we use A to B, then B to D, D to H, then H to G, G to C, C to F, and H to E. So which edges we are missing? We are missing B to E, H to F, and A to C. Let me draw a edge from C to A. We draw a edge from a node to its ancestor, so it is a back edge. Next, I can draw a edge from E to B. Either you can do from E to B or B to E. It is a undirected graph, so you can do in both way. If you are drawing a edge from E to B, that will be back edge. If you will draw a edge from B to E, that will be forward edge. Just one is left, that is H to F or F to H. Let me draw from F to H. It is a edge from a node to its ancestor, so it is a back edge. In case of undirected graph, either you can do back edge or forward edge. Maximum time we use the back edge. So this is a undirected graph and it is a traversal stack, some DFS sequence and DFS tree. Let's discuss one more example, example 2. There are two components. In previous example, there was just one component. Let's discuss how we'll trace it, how we'll do DFS traversal on this graph having two components. I'll take a stack. Let me start traversing from A. I'll write discovery time as 1 and I'll push A onto the stack. From A, I can visit C. Either you can visit E or C or D. Let me visit C. I'll write timestamp here 2 and I'll push C onto the stack. Then from C, I can visit D. I'll write timestamp as 3 and I'll push D onto the stack. Now for D, all adjacent we already visited, A we already visited, C we already visited. So we'll backtrack. When we'll backtrack, we'll pop it. I'll write number here 4. This is the finishing time. Then I'll backtrack to C and I'll check is there any adjacent left for C? Yes, F is left. So from C we can visit F. I'll write number here 5 and I can push F onto the stack. Then from F I can visit B. Here I'll write number 6 and I'll push B onto the stack. Then from B I can visit E. I'll write number here 7 and I can push E onto the stack. Now just check any adjacent of E is left. No, all are visited. So simply we'll pop it. I'll write 8 here. Then I'll pop B. I'll write 9 here. Then I'll pop F. I'll write 10 here. Then I'll pop C. I'll write 11. Then I'll pop A. I'll write 12. Now we visited A to E. One component is done. Next we'll do for the outer part. Let me start from G. You can start from any vertex. So let me start from G. I'll push G onto the stack and I'll write your number 13. Then from G I can visit H. I'll write number here 14 and I'll push H into the stack. Then from H I can visit I. I'll write number here 15 and I'll push I onto the stack. Then from I can visit J. I'll write number here 16 and I'll push J onto the stack. Now after J no adjacent is left, all it is a dead end. Now we can do backtrack. We can pop J and I'll write number here 17. This is the finishing time. Then I can pop I and I can write number here 18. Next I'll pop H and I'll write finishing time as 19. Next I'll pop G and I'll write finishing time as 20. And I'll pop G from the start. So this is the DFS sequence with timestamp. I discussed the DFS traversal. Now I'll discuss the DFS forest. There are two components, so there will be two DFS tree. Two DFS tree means it is a DFS forest. I'll start from A. From A, I can visit C. So C will be child of A. Then from C, I can visit D. So D will be child of C. Next from D, I'll backtrack to C. And from C, I'll visit F. So F will be child of C. Then from F, I can visit B. B will be child of F. Then from B, I can visit E. Now E will be child of B. So this is the DFS tree for the first component. Next, I need to construct DFS tree for the outer component. Now from G, I can visit H. So H will be child of G. Then from H, I'll visit I. I will be child of H. Then from I can visit J. So J will be child of I. Now this is the DFS forest for this graph. Now I need to add back edge or cross edge or forward edges. Now just check which edge we used. A to C we used, C to D we used, C to F we used, F to B we used, B to E we used. Then which edge we missed. The edges which we are missed, that can be back edge, cross edge or forward edges. Which edges we use? These are the tree edges. Now D to A, that is not present in the DFS tree, so I'll add a edge D to A, that is a back edge. I'm adding a edge from a node to its ancestor. So this is a back edge. Next I can add a edge from E to F. So E to F, that is also a back edge. You can also do from F to E, but generally we do back edges in case of undirected graph. Next I can add a edge from E to A, that is also a back edge. I can also add a edge from J to G, that is also a back edge. Or you can say this is a decorated DFS forest. I include the tree edges and back edges. I discussed two undirected graph. First one was one component. Second example is two component. Let's discuss one directed graph that you can understand what is tree edges, back edge, cross edge and forward edges. In case of directed graph, we'll use all type of edges, all 4 edges. Let's first do DFS traversal on this graph with timestamp. Let me start from S. I'll write 1 here and I'll push S onto the stack. Then from S, I can visit either W or Z. Let me visit Z. I'll push Z onto the stack and I'll write number here 2. Discovery time. Then from Z, I can visit either Y or W. Let me visit Y. So I'll write number here 3 and I'll push Y onto the stack. Then from Y, I can visit X. I'll write number here 4 and I'll push X onto the stack. Then from X adjacent is Z we already visited. So we'll backtrack. When we'll backtrack, we need to pop X from the stack and we'll write number here 5. This is the finishing time. Then we'll check, is any adjacent of Y is left? No. So we'll pop Y and we'll backtrack to Z. Here I'll write finishing time as 6. Next we'll check, is there any adjacent of Z is left? Yes, W is left. So from Z we'll visit W and I'll write number here 7. Also I'll push W onto the stack. Next check, is there an adjacent of W is left? No. W adjacent is X, I already visited. So I will pop it and I'll write the number 8 as the pop sequence or finishing time and I'll backtrack and I'll check, is there any adjacent of Z is left? No. So I'll backtrack. I'll write number 9 here and I'll pop. Then I'll backtrack to S. Is there an adjacent of S is left? No. So I'll pop this. I'll write 10 here. Now this part is left. We can start from any vertex. Let me start from T. I'll write 11 as the discovery time and I'll push T onto the stack. Then from T I can visit either U or V. Let me visit V. So I'll push V onto the stack and I'll write number here 12. Then from B, no adjacent is left. B adjacent is S and W that we already visited. So I'll backtrack. I'll write number here 13 as finishing time and I'll pop B. Then I'll go back to T and check, is there an adjacent of T is left? Yes, U is left. So I'll visit U. I'll write number here 14 and I'll push U onto the stack. Then check, is there an adjacent of U is left? No, T is already visited. So I'll pop it and I'll write finishing time as 15. Next I will backtrack and I will check, is there an adjacent of T is left? No, all are visited. So I'll pop T and I'll write number as 16. This is our finishing time. Now DFS traversal is done. Next I'll do the DFS forest. So S will be the parent as we started visiting from S. From S I visited Z. Z will be child of S. Then from Z I visited Y. Y will be child of Z. Then from Y I visited X. So X will be child of Y. Then I backtrack from X. Then I backtrack from Y and from Z I visited W. So W will be child of Z. Then I backtrack from W, then I backtrack from Z. Now this part is done. Again I will create another node T and from T I'll visit B. So B will be child of T. Then I will backtrack to T and from T again I'll visit U. So U will be child of T. So this is a DFS forest for this graph. It's not decorated, just tree edges are there. Now I will add back edges, cross edges and forward edges. Now just check which edges are present. S to Z is present, then Z to Y is present, Y to X is present, Z to W is present. Then T to V, T to U is present. Now which edges are missing? That will be our cross edge, back edge or forward edges. This edge I can add. Here direction is there S to W. So edge will do from S to W. That will be our forward edge. Then I can add a edge from X to Z. It is a directed edge from X to Z. So I'll add direction and this is a back edge. Then I can add a edge from W to X. This one, W to X. Neither W nor X is ancestor of other. So this is a cross edge. Then I can add this edge U to V. U to V, that will be a cross edge. Neither U nor V is ancestor or descendant of other. They are at same level. They are both child of T. So this is a cross edge. Then I can add a edge from U to T. This one. T to U is a tree edge. U to T is not a tree edge. This is a back edge. Then I can add a edge from V to S and V to W. V to S, that is a cross edge. Neither V nor S is the ancestor or descendant of other. And V to W is also a cross edge. Now just mark from the DFS tree, we can say whether a graph is connected or not. From this DFS forest, you can say the graph is not connected. There are two components. And also you can say there is a cycle or not. If back edges are present, then there is a cycle. Here back edges are present, here back edges are present. So in the graph, cycle is present. So this is the application of DFS, that we can check connectivity, whether it is connected or disconnected, and we can check whether there is any cycle present or not. In today's lecture, I discussed different type of edges of DFS forest. Also, I discussed 3 example with its traversal stack and DFS forest. In next lecture, I will discuss parenthesis theorem and application of DFS. If this lecture is helpful for you, please like and subscribe. Thank you.